All right, we're going to start the next chapter, chapter 15. Uh-huh.
You posted online that you were going to collect the labs. Which one? Because there's a lot that you haven't taken.
Collect the labs. Did I post online something about collecting labs?
Yeah.
On Piazza? Or did somebody else post it?
Maybe it was someone else.
What's on us?
What's that on it? What you
About the
said?
labs?
Lab hire went to go number 8.
This question's going to go over the labs at all, like the calculations or the equations that we had to figure out.
Yes. For the titration lab?
Yeah, and the one before that, I think too.
Oh, this, you mean this one? What lab is due November 4th?
Yeah, I didn't read it all the way. Just say done.
Yeah. For all of us.
What labs do we have outstanding? Well, we have the titration lab. We're gonna talk about the titration lab briefly before you guys turn it in. Calculation takes less than 5 minutes.
Are you taking any of them?
The titration lab,
Is it the
yes.
one we did last week?
Yeah, that's the one we did last week. The one we did before, we did a couple of labs. One was the chemical reactions lab.
Yeah.
I'm not collecting that one.
Okay.
Yeah. That one is the one you write in your notebook with the observations. I'm not collecting it, but I'm still going to look at it. I'm going to look at your notebook. I'm not sure when. Yeah, so I'm going to take a look at your notebook and then check it at that time. And then what was the other lab? That,
Yeah.
So just a lot of
experiment 6, we had experiment 3 and experiment 6, which was the chemical reactions lab. Experiment 6, you had to write the equations for those. Experiment 3 was just strictly observations. You know, this ion plus this ion yields precipitate or something like that. Experiment 6, I wanted to collect the reactions for that because you had the C. I made this lab longer. Do you guys recall this? If you look at the report sheet for this particular lab, experiment 6, they just asked for the net ionic equation. That's it. But I didn't want just the net ionic equation. I wanted the complete equation, the ionic equation, and the net ionic equation. And so I'd asked you to do all 3 of those. We did some on the board too. Do you recall doing those?
Can you just post that which you're going to be looking
I'm sorry?
at? Can you post which ones you're going to be looking at so I can make sure I remember? Just post like I'm going to look at and I'm going to collect which ones.
Well, I'm going to just look at experiment 3, but I'm going to collect experiment 6 and experiment 10, which is the titration lab. Those ones are going to be collected, but I haven't assigned a due date for those yet. So you still have time. Yeah, 6 and 10. 10 you can turn in tomorrow. It's so easy to finish. It'll take you less than 5 minutes to do the official calculation, but we might do one extra calculation on top of that. Experiment 3, I'm going to check out of your notebook.
So for experiment 6, I know that there was a lot of stuff on it, and some of it we didn't.
Yeah, we didn't do all the reactions though.
So what we need to turn in is the equation and the net ionic equation.
Well, let's do a reaction from experiment 6.
It's the one where we were
this is one of the reactions you did, experiment 6. And so what I wanted was the CE. So the CE for this particular one, this is just a single replacement. This fits the pattern here. The single replacement, okay. In fact, all these ones fit the pattern. So this would be it. And then they didn't want the CE in the report sheet. What did they give you? I didn't bring my lab manual. They just wanted what? Did they want the net ionic, or what did they want in the report sheet? Just the equation. Okay, this is the equation here. But I wanted a little bit more. And the little bit more that I wanted was the driving force. Did anybody have this written down, or nobody? I want the driving force. What the driving force is. What is the driving force? More active, less active. Driving force. And then I wanted the ionic equation. This would be the ionic equation, zinc solid plus 2H plus 2Cl minuses yield Cn2 plus 2Cl minuses plus H2 gas. Then I wanted the net ionic equation, NIE, which would be zinc solid plus 2H plus yield Zn2 plus H2 gas. And so for this particular experiment, I wanted the 3 equations plus the driving force. And so this is why I said don't do it in the report sheet, do it in your notebook so you can have enough room, because they don't give you enough room on that report sheet to do it. We didn't finish all the reactions for experiment 6. So just do as many as you can, and I'll base it on that. These, by the way, are very good practice for the final exam. You can do the CE, driving force, ionic E, and then IE. You're going to be well prepared for the final. So I'll probably collect experiment 6 closer to the final exam, so it's fresher in your memory.
So
remember.
for tomorrow, then you're going to be checking experiment 3 and 10.
No, I'm not checking experiment 3 tomorrow. Tomorrow's a kind of busy lab day, so, and you're going to have to take a lot of observations tomorrow.
So you're not gonna take 10 here then, right?
10, it just takes a few minutes to finish. So I haven't decided it. And
I think you should just wait on a minute.
all right. Yeah, 10. Maybe it looks more intimidating than it really is. It's really simple calculation to finish. It's like something that you can whip out very quickly. In fact, I wrote the equation on the board. I don't know if did anybody write the equation down? The calculation for the molarity of the sodium hydroxide? Nobody wrote it down? You took a picture? Okay, if you took a picture, then just plug in the numbers. It doesn't take time at all. Then you're done. Yeah. Yeah, hopefully you got a pic. Well, even if you didn't get a picture of it, somebody did. And you can maybe ask somebody what the equation is. But even if you didn't get a picture of it, we can go through the calculation. It's so fast, so we can do it quickly. Chapter 15, should be labeled gas mixtures first. And then second should be gases, liquids, and solids. So there are really two major topics in this chapter. First is gas mixtures. All right, so let's talk about gas mixtures. So what's a really common gas mixture you encounter every day? Air. So let's do air. For example, air. What do we want to know about air? We want to know its composition. What is the composition of air? There are different ways of expressing the composition. Percent by mass. Percent by mass composition common for air. Let's say you had 100 grams of air. How many grams of nitrogen is that? Is it easy to weigh 100 grams of air? No. And so typically for gases, we don't really, you could weigh 100 grams of air. When you buy helium, you usually buy it by the pound or by the gram, 500 grams of helium. So to compress it into a tank. But percent by mass is not common. Not common, but it's easy to figure out. Not common, but easy to determine. Instead, what do we see? Yeah, like for example, yesterday we saw percent composition by volume. I'm going to keep the numbers simple, like 21.496% oxygen by volume. So we'll keep it simple here. So percent by volume. Percent by volume, if I'm just going to keep the number simple, we'll just say air is 80%, the other one, nitrogen, and 20% oxygen. Therefore, if I have 100, let's say I had 100 liters of air, in that 100 liters of air, I would have 80 liters of nitrogen, pure nitrogen, and 20 liters of pure oxygen. But we also know that volume is directly proportional to the number of moles. And so we could have percent by moles. I started off with percent by volume initially, but percent by mole is fine. That is, if I had 100 moles of air, or 100 molecules of air, then 80 molecules would be nitrogen, 20 molecules would be oxygen. And so it's going to be 80-20 again. 80% nitrogen, 20% oxygen. Although these percentages mean different things. One's, for volume in liters, the other's for particles, molecules, moles of molecules. There's one more that we're going to deal with, and that's percent by pressure. Percent by pressure, it's going to be the same number. It's going to be 80% nitrogen, 20% oxygen. The percent by pressure. And so these are all different ways of expressing the composition of air, except this one is always valid. The other two are not always valid. So the other two cannot be simultaneously true. And so the percent by volume and the percent by pressure, these cannot simultaneously true. Simultaneously true. One is true, the other has to be false. Which one is true depends on how you want to look at the gas. If you want to look at the gas in terms of Avogadros, then this is true. But if you want to look at the gas, and Avogadros we talked about, Avogadros is stoichiometry. So Avogadros is like this. If you have 1 liter of methane, you will need 2 liters of oxygen because it reacts in a 1-to-2 mole ratio. You'll need twice as much oxygen. So that would be Avogadros. You did that. Percent by pressure, this is called Dalton's. And again, one has to be true, the other has to be false. We can flip it because we can visualize gas mixtures either as percent by mole. Percent by mole is easy. You look at the number of molecules here, 80% of the molecules would be nitrogen, 20% of the molecules would be oxygen. And so that's easy. So if I had 100 molecules, then 80 of the molecules will be nitrogen. And 20 out of that 100 will be oxygen. That's always true. And so when we're visualizing a gas mixture in terms of mole or molecules or atoms, this would be it. Okay, but what if we're visualizing it in terms of Avogadros or Daltons? So what we're going to do is we're going to put some numbers here. And so let's look at an air sample. And this air sample is going to be 100 liters. And the pressure of this air sample is going to be at 1 atmosphere. And so let's say I have a box. This box is 100 liters of air at 1 atmosphere. That's like the air in this room. Just take 100 liters of it. All right, the 2 ways of visualizing this mixture are like this. Avogadros would visualize this mixture like this. Avogadro says, out of that 100 liters, how much of that is nitrogen? 80. So what Avogadros is going to do is he's going to say 80 liters of this is nitrogen. So I'm going to have 80 liters nitrogen. That. And so what I'll do is I'm going to separate the green from the red, and I'll put all the green into an 80-liter container. It's going to be just as dense as it originally was. I mean, I'm getting rid of the red, which is 20%. And so this is going to be 80 liters of nitrogen, and the pressure is going to be 1 atmosphere. Okay, and then how much oxygen do I have? I have 20 liters of oxygen. Well, it's a smaller box. Because I have fewer molecules is not going to require as big of a box. And so this is going to be 20 liters of nitrogen, and the pressure of the, 20 liters of oxygen. The pressure of the oxygen is going to be 1 atmosphere. And so the way we visualize an Avogadros mixture is like this. If I take 80 liters of nitrogen and 20 liters of oxygen, so 80 liters of nitrogen plus 20 liters of oxygen is going to give me how many liters of air? 100 liters of air. Air is the mixture here. However, this is kind of funny. If I take 1 atmosphere of nitrogen and 1 atmosphere of oxygen, how many atmospheres of air will I have? Should I have 2 atmospheres of air? No, it's because of the way I'm adding the boxes here. I'm going to end up with 1 atmosphere. So 1 atmosphere plus 1 atmosphere gives me 1 atmosphere. That's because the pressure is generated by the collisions. And so if I look at the number of collisions per unit area here, it's the same as the number of collisions per unit area here, which is going to be the same as the number of collisions per unit area here. Although, you know, the green is going to be spread out more and the red is going to be spread out more. Now they have combined collisions, which is going to generate the same pressure as what we had before. So something like this. Okay, so this is Avogadro's. Avogadro's just basically says that the total volume is the sum of the individual volumes here. So if I take 1 liter of methane and 2 liters of oxygen, I'm going to end up with 3 liters of mixture. 3 liters of mixture. All right, let's take a look at this in terms of Daltons. Daltons, the way we visualize Daltons is like this. 100 liters of air consists of 100 liters of nitrogen. So this will be 100 liters of nitrogen. So I'm just going to get rid of the oxygen. So if I take this 100 liter box here and get rid of the oxygen, am I going to have as many collisions with the wall? No, because the red molecules are no longer there. They're not going to be colliding with the wall. And so I'm going to have 100 liters of nitrogen, but the pressure is going to be lower because there are fewer collisions. And in fact, we're missing 20% of the molecules. 20% of the molecules would be the oxygen, so therefore the pressure should be 20% less. We only have 80% of the molecules left, and so the pressure is going to be 0.8 atmospheres. And so I'm going to have 100 liters of nitrogen at 0.8 atmospheres, plus I'm going to add 100 liters of oxygen. But now, you know, 80% of the molecules are gone. All the green molecules are gone. And so the only collisions I'm going to have are the red molecules. Well, if 80% of the molecules are gone, then the pressure is going to be what? 20% of the molecules remain. The pressure is going to be 0.2 atmospheres. So what I'm going to do is I'm going to take 100 liters of nitrogen plus 100 liters of nitrogen, and that's going to give me how many liters of air? Well, 100 liters of nitrogen plus 100 liters of oxygen is going to give me 200 liters of air. No, it's going to give me 100 liters of air. And so now I'm going to put all the molecules into one box. If I put all the molecules into one box, then the pressure is going to be higher because now all the molecules are crowded into one box. In fact, the pressure is going to go up to 1 atmosphere. And so in Daltons, 100 liters of nitrogen plus 100 liters of oxygen equals 100 liters of air. However, 0.8 atmospheres of nitrogen plus 0.2 atmospheres of oxygen is going to give me 1 atmosphere of air. So in other words, in Daltons, the pressures add up. That is, the total pressure is equal to the sum of all the individual pressures. That's Daltons. And so we can summarize that mathematically here. We'll do that. This. Avogadro's basically says this, that the total volume is equal to the sum of the individual volumes. That is the volume of the nitrogen plus the volume of the oxygen. But something can't change here. What can't change? The pressure. And since it can't change, we call the pressure a constant. The pressure is constant. So all the pressures are the same, the volumes are different. That's Avogadro's. If we look at air, we can look at air, the exact same mixture, from a Dalton's perspective. From Dalton's perspective, then the pressures add up. That is, the total pressure is equal to the sum of the individual pressures. So we look at the pressure of the nitrogen plus the pressure of the oxygen. And we just add up the two pressures. Here. But we have to make sure that something's constant. What is constant? Volume is constant. So this is why they cannot be true simultaneously. One requires the pressure to be constant, the other requires the volume to be constant. In other words, how we visualize it. Do we visualize it as being 100 liters plus 100 liters gives us 100 liters? Or do we visualize it as being 80 liters plus 20 liters gives us 100 liters? That's the way. And that's the difference. We can visualize it either way. Either way is fine. For us, it's probably easier. You know, what's easier? If you're going to mix methane and oxygen, is it easier to mix, let's say, 1 liter methane and 2 liters of oxygen? Or is it easier to mix 1 atmosphere of methane and 2 atmospheres of oxygen? What do you think is easier? The first. And so this is why in stoichiometry we do it the first way. We use Avogadro's. But the first isn't always the easiest. Sometimes it's easier to use Dalton's. And so the chapter starts off with Dalton's law of partial pressures, but I wanted to review Avogadro's, which is discussed in the previous chapter. But Dalton's law of partial pressures is that the total pressure is the sum of these individual pressures. These individual pressures we call the partial pressures. So this would be the partial pressure of nitrogen, partial pressure of oxygen, however many gases we have. I just picked the 2 biggest gases in air. There are more gases here, but okay. But what does this say? The volume has to be the same. Well, it doesn't really say that anymore. The volume has to be the same. So a scientist sets up an artificial atmosphere with 4 gases. So he's got a container, puts in 0.78 bars of nitrogen, 0.21 bars of oxygen, 0.009 bars of argon, and 0.025 bars of water. What is the total pressure? Oh, they didn't mention anything about the volume, but we're just going to assume that the volume is the same, right? When you make a gas mixture, you make it in 1 container. So we just add up the individual pressures. We add up the individual pressures here, this 4 gas mixture, and we end up with a pressure of 1.02 bars. Hey, a pressure of 1.02 bars. That means this is that means about 78 out of 100 is nitrogen. About 21 out of 100 is oxygen. What kind of artificial atmosphere is this? This has got to be artificial air. This is artificial air. This person just tried to make artificial air. Would you breathe it? It's artificial. I don't know. I'd rather breathe natural air than artificial air, I think. Well, people are making artificial atmospheres, all kinds. So when they package meat, or package vegetables, or package fruit, they want to do a modified atmosphere. When they do a modified atmosphere, they change the ratios of gases. So maybe things stay or look fresher longer. All right, but anyway, we can see with the pressure, this is about 70, or we'll just call it 80% nitrogen by pressure, 20% oxygen pressure. Well, you know, that percentage is the same that volume would have, you know. If we kept the pressures the same, like all the gases at 1.02 bar, then the volume of nitrogen would be 78% of the total, the volume of oxygen would be 21% of the total. Mole percent would be the same number as well. All right, they're gonna mix this green gas plus the pink gas is gonna give us the orange gas. So let's take the green gas, add it to the pink gas, and we'll get the orange gas. What type of mixture are they visualizing here? Well, they're taking 1 liter of nitrogen, actually this is not a green gas, 1 liter of nitrogen plus 1 liter of oxygen. So if we take 1 liter of nitrogen plus 1 liter of oxygen, and we get how many liters of mixture? 1 liter of mixture. I don't really like this slide because, you know why I don't like this slide? It's because that's not really 1 liter, is it? It's a 1 liter flask plus this elbow. I don't know how much volume that elbow is. But is this a constant volume mixture or a constant pressure mixture? This is supposed to be a constant volume, but the volume doesn't look the same in all three. Do you see the volume is different? And so what you have to do is you have to ignore this here. This is why I like these fixed boxes. The volume's easy. You ignore that and just use a mechanical pressure gauge or something like that. You don't use a manometer like this, otherwise the volume is going to change. You know. Okay, so if we take 1 liter of nitrogen plus 1 liter of oxygen, that's going to give us 1 liter of mixture. Well, what has to change? Well, the pressure's got to change, right? And so, you know, we're going to cram this all into one flask. The pressure's got to go up. How much does the pressure go up? Well, the 1 liter of nitrogen has a pressure of 186. The pressure of oxygen is 93. And so if we mix both of those together, we're going to get collisions from both. The collisions from nitrogen at 186 plus the collisions from oxygen, 93, gives us a total of 279. So this is a Dalton's type mixture. Dalton's type mixture, 186 plus 93. So this is 279. There are other instances where visualizing things as Dalton's mixture is a little bit easier than other ways of doing it. This is gases generated in the laboratory. Before I do that, let's do this. Here you see the mixture as being a Dalton's mixture. Can you draw this as an Avogadro's mixture instead? How would you picture this or visualize this as being an Avogadro's mixture rather than a Dalton's mixture? So why don't you give that a try? I'll give you a few minutes to jot it down on paper and see.